Hey everybody, this is Matt Morgan. In this lesson we're going to talk about boiling and freezing points of ionic solutions. This is from chapter 12 in Wiley. We will review some past concepts for boiling point elevation, freezing point depression. We'll talk about electrolytes versus non-electrolytes and how those calculations are different, calculating our temperature change for electrolyte solutions, and then we'll work an example from Wiley. That'll be the test bank question 12.078. So we've seen that dissolving a solute into a solvent will raise the boiling temperature and decrease the freezing temperature of our solution. It makes it liquid longer. The formulas for calculating these changes are our freezing point depression, delta TF, is our freezing point depression constant times the molality of the solution, and our change in the temperature of our boiling point is calculated as our boiling point elevation constant times the molality. The two formulas are very similar. They work great for non-electrolyte solutions like glucose and ethanol. But ionic solutions are a little bit different. When an ionic solution dissolves, it breaks up into positive and negative ions. Let's look at sodium chloride. When an ionic compound dissolves, we get our component ions. Sodium chloride breaks up when it dissolves into sodium ions and chloride ions. So 1 mole of dissolved sodium chloride gives us 2 moles of dissolved particles. These colligative properties, boiling point elevation, freezing point depression, depend only on the number of dissolved particles. So we get more of an effect from an ionic solution. We quantify this by putting an additional term into our delta T calculations. We call this term the Van Hoff factor. It's represented by the letter I. So our equations become the change in the freezing point is I times Kf times the molality. Our change in boiling temperature, I times Kb times the molality. Ionic solutes give you more of an effect, a greater change in your boiling and freezing temperatures. Calcium chloride is used to de-ice sidewalks and driveways and roads because we get 3 ions for every, or we get 3 moles of ions for every mole of dissolved salt. It has an I, or a Van Hoff factor, value of 3. So let's look at our example problem, Wiley Test Bank question 12.078. This problem asks us to determine the freezing point of a 3.4 molal solution of potassium nitrite. We remember from Chem 1 that this ionic compound dissociates into potassium ions and nitrite ions, NO2-. This means our Van Hoff factor is 2. The formula for finding our freezing point lowering, delta TF, I times Kf times the molality. Our freezing point depression constant is 1.86 degrees C per molality. That would be given if it were an assessment. The molality is given as 3.4. So all we have to do, we have all of our terms. Let's just plug them in. Delta T, I times Kf times M, 2 times 1.86 degrees C per molal times 3.4 molal gives us a delta T of 12.648 degrees C. Rounding to 2 significant figures gives us 13 degrees C. Our 3.4 given molality determines the number of significant figures. Now they ask for the freezing point and not delta T. So our answer is not 13. The normal freezing point of water is 0. So our temperature change is 13. Our freezing point decreases. So our final answer is minus 13 degrees C. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.